In a series circuit, the current was constant and used as a reference. In a parallel circuit, we're going to use the voltage as the reference, and we're going to look at the currents that flow in the circuit. So here we've got an inductor and a resistor in parallel across 230 volts. Both the inductor and the resistor will get that 230 volts, and we'll get an inductor current and a resistor current. And this supply current here will be the phasor addition of these two. Like in the series circuit, the supply voltage was the phasor addition of the two voltages or three voltages. This is all to do with the current. So the current in the resistor is going to be just Ohm's law, V over R, 230 divided by 20 gives us 11.5 amps. Current in the inductor, 230 divided by 10 gives us 23 amps. And the phasor sum of these currents will give us the supply current. So we're going to take voltage as our reference. We use 1 centimeter to equal 4 amps. And there's my resistive current that's in phase with the voltage. And there's my inductive current that lags the voltage. Remember, in an inductive circuit, the current lags behind the voltage by 90 degrees in a purely inductive circuit. We're going to make a parallelogram, and then we're going to find the resultant here. And the resultant is a length of 25.8 amps. We can check that mathematically. We can do IR squared plus IL squared. So Pythagoras, this squared plus this squared, all square rooted, will give me this length here. So we've got 11.5 there, and 23 gives me square root of 661.25, 25.71 amps, which is close to what we did graphically. The impedance of the circuit, well, we know that I equals V over Z, so we transpose for Z. We take the Z to the top and bring the I down. So Z is equal to V over I, much the same way as R is V over I. And we get 230 divided by that 25.71 that we calculated earlier, and gives me an impedance of 8.95 ohms. The power factor of the circuit is all to do with this angle here. It's the cosine of this angle. So the power factor is IR divided by IS. So in a series circuit, remember, it was R over Z. Here it's the current of the resistor divided by the current of the supply. And that gives me 11.5 divided by 25.8, 0.4457. And the phase angle, as we know, is the inverse cosine of that ratio there. And that gives me 63.53. It's lagging because it's behind this voltage reference. Anything down here is lagging the reference. And we can extend that a little bit there just to check with the protractor. And we can read that off there just as about 63 degrees there, which is close to our calculated. If we had a capacitor in parallel, much the same calculation. We find the current in the resistor, 15.33. We find the current in the capacitor, 19.17. We then find the phasor addition. So again, voltage reference using the same scale, 15.33, 19.17. Make the parallelogram, 24 amps graphically. We can work that out mathematically. We can square both of those sides, add them together, take the square root, and that gives me 24.55. Impedance again, we transpose for Z. Z is V over I, and we get 230 over 24.55, which was our phasor addition of currents, and we get 9.37 ohms. Power factor, again, it's this angle here, so it's IR divided by IS. Is IR divided by IS, and that gives me 0.639, and now it's leading, because it's leading this reference. It's in front of, if we think of the phasors going anti-clockwise, this one is leading this one. We can find the angle by doing the inverse cosine like before, and that gives me 50.28 degrees. And I can use a protractor, and just over 50 there, just over 51 actually graphically. So again, this calculation is the most accurate, but the graphical representation should be fairly close to that. If we've got three components in parallel, we've got an inductor and a capacitor, then these are going to be working with each other. These are going to be swinging back the current backwards and forwards, and so they're going to be in opposition to each other. So we'll look at that now. The current in the resistor, straightforward, V over R, 4.6. The current in the inductor, again, just V over XL, 2.875. The current in the capacitor, 230 divided by 40, 5.75. Now when we draw the phasor diagram, we can have the reference again as the voltage. The resistive current is going to be in phase. The inductive current is going to lag. And the capacitive current is going to lead. Because in the capacitor, the current leads the voltage. In an inductor, the current lags the voltage. Now what's going to happen is these two are in opposition. And so the resultant is going to be this minus this smaller one. So it's going to come down to this line here. 5.75 minus 2.875 gives me 2.875. Just coincidence. There's my 2.875 there. And now I've got my resistive current. I've got my overall reactive current. I can make the parallelogram, find the resultant, 5.4 amps. Mathematically, there's our difference between the two currents. There's our 2.875, which is that difference there. We square them both, take the square root, 5.42 amps. So that's our more accurate calculated current. The impedance of the circuit, we transpose I equals V over Z again. Z is V over I, 230 divided by 5.42, gives me 42.44 ohms. Power factor, again it's this angle here that we're interested in, it's the cosine of that angle. So we've got 4.6 and the 5.4. 4.6 divided by 5.4 gives me 0.852, and leading because this phasor is in front of this phasor reference if we think of it going anticlockwise. So 0.852 leading. And the phase angle is going to be the inverse cosine of that ratio of 0.852. Gives me just over 31.5 degrees. And again, we can look at the phasor diagram, put our protractor on there, and it's about 31 degrees.